Alright, should be recording. Better check just to be sure. Well, looks like the right icon anyway. So yes, another draft physics video presentation. DraftScience. Gotta say that on YouTube. Anyway, it would be just DraftScience, but I couldn't get that .com name, so I had to go with Draft Physics. But it really is Draft Physics. So I should have had the Draft Physics name on YouTube, because we don't do much of the other kinds of sciences. So, yeah, not much in the comments. So I think we'll do a little bit on refraction, and yeah, we'll see where that leads. It can always go somewhere. So the idea is that you have light. I guess I could do the light in a different color. I don't know if it really matters. It hits a surface. Part of it reflects perfectly, so to speak, angle in, angle out, and then the refracted bit ends up being a different angle and goes through and then is restored to its previous angle on coming back out again, and there's this time delay. And people like Bill Gates and lots of people take advantage of this. Ken Wheeler, lots of people think, oh yeah, the light slows, how's it speed back up again? These idiotic arguments, frankly, that just muddy the water. I mean, dissidents, it's really just a group, that somehow needs to be some sub-organization, within, like here you have the established, I went to MIT physicist kind of crap. I buy into anything they tell me is true. When they say, hey, we done it, I believe they did it, that kind of thing. And then you have a group below that could be full of engineers or other kinds of people that also have peer review, in the sense that group gleans out the flat earthers and the people using the bogus arguments and the nonsense. But you see this in conventional physics even. They don't even clean their own house, in the sense that you have physicists making videos on YouTube debunking other people with Photoshop, and singing songs, and it's all these jokes. They can't just make a straight up argument why you're wrong and why you shouldn't be propagating misinformation and being a liar, because that's just not a nice thing to be. But they just can't resist just buffooning. And also, I think it's partly because they don't have great answers to a lot of questions. And so part of the way to hide your lack of character or integrity in what you're saying is to pretend any complaint is a mockable complaint. Alright, well anyway, change the subject already. Alright, so that's visible enough. So the idea is, why does this happen? Alright, so the first thing to figure out is this reflection thing. So let's understand that the likelihood of this beam reflecting changes, like the more I change this angle. So you could say this has an index of refraction, or whatever the number would be, and it's also the index of reflection. No, they're two different things. Okay, so sorry. The reflective index is how much light is going to reflect off a glass surface, for example, can change depending on how thick the glass is. So, but there also, what changes is if it has a certain reflective index of, say, 5%, that's for a straight line beam. And the more I turn the beam, the more I increase the likelihood of reflection. So, like at this angle, it might be 25%. That's why when they talk about beam splitters being 50-50, they're really not 50-50. The glass has been silvered at much lower rate than that, because it's got to account for the fact that the normal is going to be that you're going to get 25% reflection just because you're coming in at a 45-degree angle. And if I increase this angle even more, there's a certain point where I'm kind of guaranteed, 100% of the light will reflect off the surface. So that sort of explains glare and a lot of different things, blah, 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 blah. So I'm increasing the amount of the likelihood of reflection. So you could ask, well, why does that happen? Well, kind of an obvious answer might be that you can understand that the electrons on the surface are spaced, because electrons don't like each other. And clearly, at this angle, your likelihood of hitting an electron is much lower, okay, coming straight down, a surface electron is much lower, and you end up hitting one down here, let's say, then your likelihood of being trapped in the material is higher, or your likelihood of being transmitted is higher if you get through this first layer of barrier. And so all you're really saying is what's the first layer? The likelihood of hitting an electron, and that's sort of your reflective index. So how far spaced are the electrons compared to empty space, and that pretty much tells you what your reflective index is. Now this surface can have more than one layer of electrons on it. See, every surface is going to have electrons, right? The atom has got the proton in the middle, and well, yeah, you can see that. And the electron outside. The electrons are always on the outside, and these are all materials that have kind of complex atoms. But even a simple atom, a bunch of them stacked together, you just end up with electrons on the outside. And there's obviously this attractive force from the proton can extend outside of the atom, so other electrons can be loosely associated with atoms. Now they can't really do that inside the material because they're repulsive. You know, there's nothing but electrons, right? When more than one atom is in a material, you can sort of understand that there's nothing but electrons on the outside. And so a free electron is quite hostile. He's not going to find a good, comfortable place to hang out, where they can hang out on the surface quite easily. So surfaces are covered with these little electrons, and the electrons are going to establish a very rigid geometry. So I suppose that's another thing to talk about, how atoms aren't what you think they are, in the sense they're not all little round things. Okay? I think quite clearly atoms are square things, atoms are hexagonal things, atoms have lots of different shapes. I guess that's not perfect there. Point and point. Anyway, lots of shapes. So anyway, that's another subject. So anyway, you can get the idea that you're increasing the likelihood of reflection, because as you're coming on an angle, you're closing the open spaces, are getting smaller and smaller and smaller. So if you take a piece of screen or something, you look through it, and it's very transparent. And the more you turn on an angle, the less and less transparent it's getting, because you're basically eliminating access to the empty space. So as soon as you go past this angle, the angle from the top of one electron to the bottom of another electron, as soon as you go past that angle, you've eliminated your ability to go through the empty space. Okay, and you're going to guarantee that you're going to hit an electron. You're just not going to be able to evade it. And so that sort of explains why the reflective index changes as you change the angle. Kind of a solid explanation. Now, for this here refraction thing, why does this angle change? So that, yeah, I should have a better drawing system. I'll work on it someday. Someday. We don't need this external line. All right, so why this angle? So the key would be, is that if you're understanding what I've said so far, now you know the atoms have a sort of a rigid, pretty rigid relationship between the distance between the protons and the electrons, and that pressure is balanced between them. And so, you know, there's a geometry established, a distance established between things that are harmonious, between the positive and the negative charges. That is the faux attraction, you know, created by the absence of pressure, and the repulsion created by the repulsive pressure between the electrons. The fact that there's energy between them bouncing back and forth, and if you bring them closer together, you're essentially creating more energy. All right, so they have an arrangement. Now the ones on the surface are, as stated, are kind of loosely held. So they're not held with the same strength as the electrons in the real atoms. So the atoms are tighter pressure. So you can sort of see it maybe drawn this way. We'll illustrate it. So the surface electrons are more loosely held because they're really not attached to a they're not firmly attached to a proton. So if I put the protons in here, you could sort of, the nucleus is, I think you could sort of get the idea. All right, so they're attached more loosely. So what's happening is essentially, okay, you're going to convert an angle coming in. So a line's going to be coming in one vector. Now you know that has a portion. I could write the portions in white chalk. I don't know if that really is going to matter that much. It has a portion going this way, and it has a portion going this way. A momentum. Part of its momentum can be understood as two kinds of momentum, two directions. And clearly which ones are going to, which way you can push this electron. You can't, pushing down is going to be harder than pushing this way. You can sort of get that. Or, frankly, this way. So the two portions, it's easier for the thing to move one way than it is to move the other way. And likewise, going back would be the same kind of argument. But it's that differential between the tightness of these electrons versus these. And the tightness would, you could also, I should have drawn this maybe this way, that these electrons aren't going to be lined up with these electrons. Obviously, they're going to line up staggering to those electrons. And they're probably going to do it with greater distance. So that just the idea is the looseness of these electrons and the distance is what's going to change this momentum subtly, okay, in the sense that it's going to allow more of it to be used up when it hits the electron. This electron is going to move more this way, right, than this way. That's probably the way I should have said it. Okay. And in doing that, in moving more, in being more capable of going down than sideways, right? Because it's got to line up with the original matrix. Yes. Okay, so that's what I did wrong. So, sorry. Okay, so these would line up here, in between the pressure created by the real electrons. So they would be staggered. So this distance would be consistent with this distance. But this distance up and down would be, see, now I didn't do those high enough, so I should do them up here. It's just harder to see where the right place to put them is. Alright, so that's the way to look at it. Okay, so it's easier pushing them this way, okay, because this electron's going to repel and this one's going to repel. They're going to resist that. Where going down, there's not much resistance because the electron is loosely held. It's not a very strong attraction to the proton, so they're further away. So the downward pressure is more likely to be how these two vectors. So this is the momentum. We know the momentum has this character of being able to be converted, its energy, in either one of these directions without violating any laws of conservation of momentum. And so it's basically just going to sit there and do the conversion. So this top layer of electrons will convert, okay, the portion of energy this way. More of that gets converted to this way, then this way gets converted to this way because it's easier for it to go this way. So more of its energy goes this way, and now less goes this way, and that's what bends this line towards this normal. So this line gets bent down because it's easier. When it hits, it's easier to curve it down than to go, it can't go straight across because there's more pressure this way. There's more opposing pressure this way than there is a pressure this way. So I'll make that long line or that line longer. So there's more pressure saying you can't push electrons that way and less pressure down. And so it tends to go down on that first row of electrons. And once then it has a direction, it just follows the direction straight through this matrix. So this matrix of the atoms allows it to push pressure. If you make this drawing a little different, okay, in terms of understanding, there's a matrix of electrons. It can push one electron here, which pushes this electron, which pushes this electron theoretically. The pressure would be pushed all the way through, and that's what has a speed change. So your speed change it's really the fact that for some portion of the movement, you had a regular force that goes the speed of light. But what you're really doing is pushing an electron. So you're going the speed of light. You hit an electron. The electron moves a little bit, but it moves much slower than the speed of light. Then you hit go back to going the speed of light again, and then so you're just converting electrons' movement into an increase in pressure between the electrons, and that moves the next electron, and so on and so on. But the time while the electron is moving, you're not going the speed of light anymore. You're going much slower than the speed of light, and that's what's slowing the light down. It takes time to move the electrons, so they're consuming the extra time is the fact that you're jumping in a slower car. Well, see how to say it. I mean, the force is essentially just jumping. That's what you sort of understand. It's just pressure. So it's pressure moving from between these two electrons, and then the pressure moves between these two and these two and these two. It just moves the pressure. But effectively, to do that, it has to move the electron, and the electron doesn't move the speed of light. So in spite of that error, I think the point is made. So I think that's an explanation for the refraction of light in transparent media, and the fact that these electrons are what's creating the obstacle to angled light. Light coming in at angles a little bit just bounce off the electrons. And again, the light is made of a bunch of little bits, and each little bit is an independent agent, and each time light hits a surface, it's broken. Each time it interacts with anything, the light is essentially broken as a visible photon, and you have to make it revisible by combining it with another stream of photon. And so there is no, until we make a single photon gun, which will be a huge, that'll be a gigantic advantage in testing, in experimentation, when you have a known quantity, because we really don't have any way to do that now. The only way they tell whether they have one photon coming out is they have to detect the photon, and if you're detecting it, then could be 10 photons that are coming out, and you're just seeing the one, that you remake into a visible photon. So you're pretending there's only one photon, but there's really more energy than that. But there's no way to detect it because the energy of photons is so tiny. The only way we see the energy of photons is because they can move electrons. And that's it. If it wasn't for the fact that they can move electrons, the amount of energy is so small. To move atoms, to create heat, takes a lot of energy. So you have no appreciation for just how weak photons are, because, compared to like heat or something, and heat's moving whole atoms. Giving energy to the protons and the electrons. And moving the protons is a lot harder to do than to move electrons. Electrons are tiny, protons are heavy. Right. Let's see, so is there anything else on that subject? Alright, so I'm just demonstrating that a particle model can perfectly explain the phenomenon without... No big deal. Let me just see if there was something else that I had written down. Oh yeah, I should do something on the atom shape thing. That's sort of interesting. And then there is, of course, this pattern stuff that's always interesting. This one, yeah. The lines and the tilt. So this pattern is created by that one piece of glass. The little piece is tilted. So there's like one piece of dust at one end, or more dust at one end, and so it's tilting it. And that's what's creating the line. So the least I tilt it, the less it's not flat, the fatter those lines will get. The wider they'll get. And so the more even it is. Now, whether or not I can do that by increasing the height altogether, that is, that's an experiment worth seeing, is if I actually just put little bits of some material of a known height underneath the lens and then set it on top, do I still get the same kind of tilt pattern? That is, tilting is what creates the lines. and that I can get 0 lines almost if I can get it perfectly flat, which is the interesting part. But this goes to the interferometer and how it works, because they keep arguing that interferometers work by changing the distance of the mirror. You know, moving the mirror forward and back changes the pattern, when I think it's clear that tilting, any angle that the mirror has, is hugely important in terms of it'll tell you which way those lines would be going if you're just looking at lines. So those lines are really supposed to be representations of this circle. So they're just a view cut out of a section of the real pattern that's going into space. So they're really arcs of the circle, and so they're so straight, it's implying a gigantic circle that it's creating. And so I haven't quite figured out how to illustrate that, because the particles themselves, a bunch of little particles, will create the same pattern. So this is being created just by the internal reflections back and forth between the 2 layers of glass. And the pattern in the interferometer is being created because you've broken light by passing it through a bunch of little slits. So it's not so much about the mirror, it's about the space between the mirror. You know, when you're creating a double, you know, one of these half silvered, and again, it's not half silvered, it's much less than half, because it already has to compensate for the amount of reflection, 25% or whatever it is, that you're getting at a 45-degree angle. There's a certain amount of reflection you're getting already. And so it's really only like a 25% silvered. But anyway, I already pointed that out in the previous video. So what did I want to do? Well, okay, so yeah, so I would argue that atoms are solid structures in the sense that they're real. They have real geometry. So depending on you know, it's always got the same concept. The protons are stuck in the middle through a mechanism of having 2 protons with an electron in between them. So there's actually an electron that's being the mediator, that's allowing the 2 protons to get very close together, because the protons are essentially, there's low pressure between the proton and the electron because all the energy is sent out in one of the other dimensions, low pressure, and so they'll be able to get much closer to each other. So that's the nucleus. It's got the protons combined really close. So they're doing the same thing the atom is doing, in the sense that you have electrons and protons. It's just that the nucleus, like in almost cellular nucleuses, they were cells, and it's a cell that got consumed to become the nucleus. It's like there's little, it's a subatomic structure, not too different from the atom itself. And depending on how you can arrange the electrons and neutrons and what kind of shape you're going to get of the nucleus will decide where your electrons, okay, well, electrons should be white, will find a stable condition. And so there's going to be places where there's forces that would end up repelling the electron more or less. The nucleus isn't like radiating some perfectly consistent positive, because it's a composite of positive and negatives, and more positive. Okay, I mean twice as many protons as electrons if you count the neutrons as protons. So it has twice as many positive charges, but the positive charge is not consistent, in the sense that from certain angles it's more positive, from other angles it's less positive. But anyway, and the electrons are going to orient based on that condition, and they're also going to orient based on the fact that they repel each other, and they have pressure between them. And so there's going to be a geometry to atoms. Atoms aren't just round things. They're not some kind of idea with the protons in the middle. I'm arguing anyway. And that you have some idea of a circle that the electron travels. These electrons aren't spinning around anything. So when they're shared, they're literally shared. So when this atom shares this electron, let's say, it'll share it in the sense that the other atom is going to be over there. And then it could share it by sharing 2 electrons, and then the other atom is going to be over here, you know, like this, with its nucleus. So there's different configurations or ways you line them up, and this is, you know, perfectly explains why there's such a thing as crystals in atoms, is because they do have a geometry. The crystal is in the geometry of the atom itself, not in some notion that has all this spinning junk. So that ain't happening. And by having a real shared electron, it just makes it so much more obvious that both of them are sacrificing something. By sticking together, they've essentially lowered their total mass by 1 electron, because they're sharing that electron. And that bond is so much more permanent than some idea that this electron goes way over here and this thing stays here for some reason. So even though there's no electron here, it still stays here. That doesn't seem very realistic. So I'd argue that's an intuitive reason to doubt their moving electron theory. Also, to say good reason to doubt it is the fact that you'd have all kinds of energy equations where if the electron's going this way when a photon hits it, you know, it would create a completely opposite effect as if the electron was going this way when the photon hit it. All kinds of, just makes it way too complicated, I think, to be realistic, that electrons can have all this mobility. Alright, so I don't know if that's critical to anything. I'm just saying it makes more sense geometrically that atoms have a geometry. It makes more sense in terms of locking structures together, and why is there such a difference between a piece of glass and a piece of steel in terms of one being transparent and one not being, even though they kind of weigh similar, the similar density, similar number of electrons and protons, and yet somehow one of them transmits light and the other one doesn't transmit the light. And I think that has to be because of this geometry. You know, one has a geometry where the electrons can share their pressure easily, and one has a geometry where it's can go too many different directions. Alright, anything else? Well, I'll take a pause and see if I can find something else. Alright, I guess I'll do a quickie on the right-hand rule, just because somebody brought it up. I don't know why. It's not related to the video he's commenting on at all, really. Right-hand rule is fundamental rule in electrical and electronics phenomenon and such. Yeah, so do you understand why there's a right-hand rule? No. Alright, so I'll attempt to give this some texture. So I've sort of made this argument before, and it's getting more clearer and clearer in my brain anyway. So the trick is you have a wire and you create you put a field across it. So you have a north side of a magnet here, and you have a south side of a magnet over here. Alright, and you put a current in one way, the wire goes up. You put a current in coming out of the board, let's say, and the wire goes down. It doesn't matter which one is accurate, it's, you know, close enough. And so what you're really doing is just understanding what happens in 3 dimensions, right? So you have this force is going in this direction. I mean, it's coming out. It's not there. There's no force going from the north end to the south end. That's just fallacy. There's 2 different forces, okay? And the fact is, it's acting on protons and electrons when I'm, you know, they're doing inverse thing to the protons and the electrons in the wire. They're affecting the protons and electrons in the wire. And the rule sort of is if there's a current moving through the wire, the rule changes. So where this force would just necessarily apply in 2 dimensions, so you have the dimension of the motion of the electricity, call that. Then you have the fact that there's a field pushing one way that's attracting electrons, one's repelling electrons, and vice versa for the protons. And what you're really saying is when you've used up two of the dimensions, that is, you have the current going one way and you have field pressure, well, not draw it as a straight arrow coming in from this direction, that you end up, okay, the product is the third dimension. It goes into the third dimension. So it's really a right-hand turn in the sense that I have to go pick that up. I think that's my only white bit. Oh, yeah. All right. Logistics. So much to keep track of. All right, so let me erase this. So I've argued that, so the interesting part is this, so if you could sort of understand this inverse part, that if the north and the south are doing the opposite thing to each other, and then you're having the direction is opposite, you could sort of understand that there's essentially a double negative, right? You've made not only the force change, so that's 1 minus you could put, right? Because now you're switching, you could switch this. And the other minus is you're looking from the left side or the right side, so it's a double negative essentially. So they end up pushing in the same direction. They would do the opposite thing, because they're opposite poles. So this side would tend to want to go this way, but you've got an inverse. So you've taken that arrow and moved it back up from its perspective. So looking this way, this is up, and from that direction, this would be down, kind of thing, or left or right. So you've changed what left and right is by changing what side you're coming from, obviously. And that means you're inverting it one way, and then you're inverting the pole, which is the other inversion, and two inversions, two opposites of, this is going to be that. So that's why they're both doing the same thing, is because of the opposite nature of the poles. And so what it really comes down to is, I've sort of made this argument that for electrons, when you hit it with electron force, it's a simple equation. This gains momentum, and you have a reflection straight back out. So it's completely uncomplicated when like force. And the same would be true from proton getting proton force. But if the opposite force hits, the proton force hits an electron, it gets more complicated. So the force hits, but if this particle is moving, say in this direction, let's say, so it's already got motion in this direction. The trick is that this energy, okay, ends up coming out or in of the third dimension. So instead of just creating, motion in, say, this direction, which would be the tendency, and the motion would be inside. So instead of adding motion this way and having a reflection that would go out this way. So that's the idea, the inverseness of the forces. You're really just saying the force goes into the object and it's turned, right? So I'm just saying that instead of creating forward motion, hitting it, it's basically turns the force, okay, it just perpendiculars it. But the idea is to understand is that it can perpendicular in the third dimension as well. So the in and out dimension is just as right from this force's perspective. It's just as much a right turn to go in and out as it is a right turn or a left turn to go forward and back. And so that's what's happening. So when the particle is moving, all right, the rule is it doesn't go in the direction of the movement. It goes into the third dimension. It takes that right turn. And that's why this goes up instead of left or right, in and out. It's instead of going in and out, it goes up because it's taking the third dimension. The momentum's being moved into the third dimension, up or in and out of the board. So if you have two, you have motion in this direction, you have a field acting in this direction, the force will end up going into the third dimension, the reflection and the force. I didn't perfectly explain that, but that's the right hand rule. It's right hand because of how we're establishing the premise as being always a negative current circumstance. So it's only right hand if you're using electrons. It's left hand if you're using protons. So So it just has to do with the fact that we have a preference to say this is the default. The north side of the magnet is the default, essentially, or the negative electron. And so it's only a right-hand rule if your default is what's it do in the negative state. If this current is moving this way, and into the board. And that's the default. But like I said, you just change that default, and then it's a left-hand rule. All right. But that's the motor force, and that's blah 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 blah. But it can be easily understood. You have this option. If once you're going to say that a force goes in and it's altered, it's made to go perpendicular, you're going to understand that going this way, perpendicular this way and this way, is no different energy-wise than that way and that way. In empty space, there's no up and down. It's not harder to go up than it is to go right. So both two dimensions can be utilized in terms of which way the force is expelled. But that ends up being a right-hand rule when you argue, when you set up a premise of what direction this is going, relative to some other default, like this is right, left, and this is up and down. I can't say that. I could probably say it differently. The point would be is that once it goes into the third dimension, it can come back in through the third dimension, come back out from the third dimension, and also influence things. But obviously, when you've gone to the third, when you throw something out the third dimension, it can't affect the two forces you're already acting on, which is the movement of the current in the wire and whatever field you've got it in. It's not likely to come back from that third dimension anytime soon. But anyway, could be, a million years. It could take a long time for where that force went to have any implications. It essentially can't have any implications. I mean, once you're sending, say, when this movement goes up, our argument is the force goes down. Well, this force going down really has no chance to interact with anything in any significant way, so it's essentially left the building. It's not a player anymore in terms of influencing anything, affecting anything. All right. I don't think there was any great vids, good vids. All right, electron microscope, a guy brought up. Scanning. He said electron scanning microscope, or it's supposed to be scanning electron microscope. But yeah, they have so many versions of it now. So the one thing that I found curious is just the thing, you can only find so many details, and so I'm looking for something that really dissects how the electron beam is focused. Because I'd argue this is sort of a tricky, say if you had electrons coming down, and you have one here, and you have one here, and you have one here, and they're coming down, and you want to focus them. That is, you want them all to be going like this. You want a bunch of electrons to hit one little tiny spot. So you want to take a beam that's fat, and you want to try to focus it into a little beam. How do you do that? Right? Because the problem is you can't just create a magnetic field, like an equal magnetic field from all sides, going in. So if you did that, that's not going to work, because that's like the gravity argument. Making a hollow sphere in gravity doesn't get you anything in here, so it's not going to. So if there's an electron here and here and here, you could sort of think, well, if I push from all sides, I'll end up pushing them all into the middle. But that doesn't work, because you're equalizing the force. So as much repulsion as you create going this way is going to be so much stronger than all the repulsions heading this way, and it's all going to be equal. So the amount of this whole surface doing less repulsion is going to equal the strong repulsion you have there, and so it's still going to be a nothing, a zero. So you can't create any pressure moving the electrons together. So, and this is somehow essential to how an electron microscope works, is the idea they have to take this big beam of electrons, and they have to turn it into a tiny beam of electrons. And So, and again, I'm going to argue still that I'm not convinced electrons are actually doing this, and that what it really is it's kind of like an X-ray gun. You shoot X-rays into the, high energy rays into the substance, and you knock electrons out. Yes, those are electrons you knocked out. But they don't go very far and all that kind of stuff. They just pop out and you can see them, detect them. And that's how the thing works. But anyway, it's very complicated electron microscope. So someday, yes, I hope to dissect it more thoroughly. But you have to understand all the components of it. I don't fully understand how they're accomplishing some of the things they say they accomplish. They show you a diagram and say, condenser, Does this tell you, what do you mean? How are you condensing? So anyway, so yes, I've talked a little bit about them, but it's, like I said, they are really complicated. So, not today, someday in the future. Okay. This other guy mentioned some Oregon engineer who did a traffic light timing. Traffic light timing is something people would argue till the end of time, I mean, what does a yellow light mean? Should a yellow light mean to you, oh, I have time, I can go do something still. It's not red yet. It didn't say stop. Or should a yellow light mean to you, this is the same thing as a red light. And so I'm really not allowed to be moving into the intersection, okay? It's just not a thing I should be doing because it could be red any minute now. So there's just no reason for me to think anything other than yellow light means prepare to stop. That's what everything your brain should be saying. I have to go into stop mode, not into keep, just play along and I can catch just the end of the red light. I mean, just the beginning of the red light and pretend it wasn't a warning that was telling me you can't do that. And so what he did is just say, make the yellow light longer. Okay, because people need time to slow down to turn. Well, that's not what they're supposed to be doing when the light goes orange. They're not supposed to be saying, I need to slow down to turn. They're supposed to be saying, I need to slow down to stop. And so, as long as people aren't doing the same thing, as long as they don't understand the colors the same way, you can't have one theory that works. Because half the people are saying, warning light, yellow means try to get through the curve real fast. And the other half of the people are saying, yellow light, stop. Because stop is coming. There is a stop sign, it's just far away, but it's there. It's a stop sign. It's not a go through the intersection sign, it's a stop sign. And so it's just interpretation. So there's no theory because there's no foundational premise about what the warning light means. All right, that's all I can, that's enough said, I think. I mean, people know not to, they know they wait for the green to go. So they really do understand the concept. Like yellow light doesn't mean go as soon as it turns yellow. No, they know that's not how it works. They know they're supposed to wait for the green. And it's just like they're playing this game like I can cheat when it comes to the fact that I know the stop is coming. And I'll just pretend it's not. All right. Anyway. It's not really, not really a viable subject. But anyway, everything's all horseshit. I mean, his whole point is that nobody changed, yellow light theory. And I'm not saying what he did wasn't a bad thing, just to fight the man and all that kind of crap. I mean, it was kind of crazy. Oregon has some kind of law that you can't complain about something. They have a procedure. You're not allowed to complain about it, or we'll fine you. And it's hilarious. It's like, yeah, well, that's a little unconstitutional. But the whole racket with police departments using these gimmicks to try to increase revenue, that's where it all goes wrong. All this technology is great, cameras, tickets, all that stuff, great. Let's replace the cops entirely, fantastic. Let's put cameras everywhere and just say fuck you cops, we don't need you anymore. So I'm all for that, but they always bend the system for some other purposes. It's like the military industrial complex, the government industrial complex of a bunch of government employees trying to protect their jobs and their pension checks and try to steal your money to do it, to pay their pensions. That's bullshit. I mean, raise the money honestly, you fucking crooks. Anyway. Yeah, that's enough of that. Alright. I mean, you have a durable system, then you save so much more money in the long run. You have an honest, good system, then you don't have to worry about traffic court. You don't have to pay judges. You don't have to pay all this bullshit because your system is a thief. You don't have to be sued if you do it honestly. Stupid fucks. Anyway. I mean, it's really, civilization shouldn't be this difficult. The concepts are pretty simple, and it's just that the fact is that the people are cheaters, and they want to keep all the cheats they're taking advantage of, and they want to deny everybody else the right to cheat. It's just such bullshit. They're just such hypocrites. All right. Anyway, people suck. I've told you that theory before, right? My theory that people fucking suck. Yeah, that you really can't, gratuitously annihilate enough of them. But anyway, it's my theory. There will be no tears in the universe when humanity no longer exists. Yeah, nothing will cry for them, Argentina. Anyway, till next time and such. And so forth and whatnot.